All right, greetings all you researchers. My name is Dr. Casey Smith, and I'm here to introduce the first sort of intro training to the use of our Raman AFM system. We're housed right now in Roy F. Mitty building, room 1203, and the first thing that I want to do is point out some of the important components on the system so that you know where to go lay eyes on them as you're doing things like the pre-flight check or any other sort of troubleshooting that you might have to do. The first of those components is the actual detector back here. So this is basically a CCD detector, or a charge collection device. And the two key things that you'll need to pay attention to are little LED indicators right here. As long as both of these are green, the system has power and the detector is at the appropriate temperature. So as long as those are green, this detector is ready to rock. All right, next set of important component pieces that you'll need to be able to identify. Down here, below this little rack here, we have the three power supplies for the different lasers. So there are three lasers on this system. One of them is a 633 laser, which has a tube that's integrated inside the box. And then the two other lasers, the 532 and the 785, are mounted on these two plates. So these little optical plates are basically aligning the lasers so they go into this diversion tower, and mirrors move up and down inside here to select for which specific laser line you want to end up utilizing. The power supplies for the lasers are down here. All of them have some sort of a key that you'll have to turn on. And then depending upon which specific power supply you're trying to turn on, you may or may not also have to hit a button to make it go live. So this is where you'll turn on lasers. Right next to it, you see a black box. Green LED is a good sign. This box is the controller for the Marhauser stage, which is essentially the XYZ stage that's mounted on the front side of the unit. This is basically how you can move your sample underneath the optical objectives in the microscope stage. And then last one on the back side of the system here, you have basically the LabRAM controller, which is your main interface between this LabRAM Raman system and the PC, which you use to sort of control it via the software. So the LabRAM controller has a power supply switch, which is right here. It should be on at all times unless you've been directed to turn it off by a staff member. And the way that you would know that everything was hunky-dory and happy with the LabRAM controller is up inside this little well that you see right here behind this laser diversion tower, you can see a set of green LEDs, and there are 4 of them. As long as those are all lit up, then the LabRAM controller has communications back with the box. Okay, last couple of pieces that you're going to be spending a lot of time interacting with are all here associated with the navigation system on the optical microscope. So as you may notice, right, there are no objectives here because there's no circumstance where you'd want to be looking through microscope objectives that are funneling laser light, right? You never want to focus that into your eyeballs. So you're going to be using a video feed on the monitors here in order to see what your sample looks like. The turret that you utilize for changing objectives is here. There's a knurled portion of it, and you just basically rotate that until you get the objective of choice into its sort of centered position. There are 3 objectives on this system, a 10x, a 50x, and a 100x. So turret moves up here. The course adjustment for the height of the stage is located here on the left-hand side, and it's extremely important to remember as you grab it with your left hand, thumbs on top, the thumb has to move towards you in order to move the stage downward. So the safe motion on this guy, and again, this is when you're working at a, sample is here, objective is here, you don't want to make the mistake and accidentally move up and crash into the objective. So always move this guy down by grasping the knob and rotating your thumb towards you. Okay? By the same token, and even sort of more risky, is when you have a high magnification objective and you're at a very, very close working distance to your sample. In that case, you're not going to use the coarse adjustment to move in Z. You're going to use the fine adjustment, which is actuated with this knob on the Marhauser controller joystick. So in addition to translating me in X and Y to move my stage in this direction, the knob will rotate to move me in Z. The knob is proportional control, so the further you turn it, the faster it goes. And please keep in mind that, again, there's a safe direction to turn this knob to make sure the stage goes down, and that safe direction is clockwise. So it's always safe to turn this guy clockwise when you're searching for focus, but don't arbitrarily turn it counterclockwise if you don't know exactly where you are in your optical focus. Last thing I want to point out here is just down here below, we have our top side and bottom side illumination. That's the white light illumination that we can send through our scope, either from the top side or illuminated from the bottom side, depending upon the nature of your sample. And that's these 2 boxes here. Please don't turn them past about 8 the position 8 here, which is roughly 80% of their drive power. And that just prolongs the lamp life. Now that we know where all the critical components on the LabRAM Raman unit happen to exist, we can go through the first stage of the SOP, which is the pre-flight check. Some of the things that I ask you to confirm before you actually start using the instrumentation are as follows. Number one, please verify that the CCD detector is on, that is, it has power, and that the Peltier unit that's responsible for its cooling is also satisfied. And the way that you would know is you would see power and temp little LEDs are both illuminated. So if that's ready to go, move on to your next one. The next thing I ask you to determine whenever you walk up to the system to utilize it is, are all laser sources off? So essentially down here you should see the keys all in vertical positions and no LED lights indicators are on. So that's the status we ask you to leave it in when you're done using the tool, is all lasers off. So when you come in to use the tool, I need to know if the last person did that correctly. Marhauser stage controller should be on with a green light lit. And then again, the LabRAM controller should be on, and if you put your camera right about here, you should be able to see up inside this little hole, there's a few green LEDs that are inside there that basically indicate that it has communication back to the PC and that you can in fact control the instrument. All right, and then finally we check around here on the other side, again, sources. We always want to leave these off to prolong their life. The top and bottom illumination boxes for your microscope feeds are both all the way in the off position. So these guys are all the way off. So what we ask is that if you find the tool in a state where you can't verify that these things are as I've mentioned they should be, please inform SRO staff either via email or via FOM, but just you need to let us know that the previous user didn't idle the tool properly, and so we can go correct that action. All right, so on the Raman system, we like to make sure that we have a safety declaration in place so that everybody understands what's dangerous about this particular unit, and in fact we do that for all of our instrumentation. So what is specifically dangerous about the Raman? The Raman unit is utilizing 3 different class 3B lasers, which can lead to intense eye damage if you're not being careful. What you have to remember about the use of lasers is as follows. As soon as you send them through microscope objectives, you're going to drop down the overall intensity compared to just at the exit aperture of the laser. So staying in a paradigm or an operational environment where you keep the laser light confined to the microscope optics is by far the smartest option, and that's exactly what this system does here. So under no circumstances should you ever attempt to view the laser beam or get inside the optical cavity. Just let the lenses and mirrors and filters and things do their thing inside the optical pathway, and just work on the laser that's exiting from the microscope objective. The other thing that's important to keep in mind is that distance will basically drop the intensity rather drastically as you move further and further away from a source. So try to maintain at least an arm's length from the sample where the laser light could potentially bounce off in any time when the laser light is going to be on and illuminating the sample. And then a few other things to kind of keep in mind that are just general housekeeping things with lasers is be careful about some of the reflective surfaces that you might encounter as you're working inside the space, or those that you inadvertently bring into the space. So for instance, my little lanyard, right, could have a reflective surface right here on this polished portion. Or if I had a ring or some little flashy bit on my watch. So getting all that loose bling off of your body before you start working around open beam lasers is important. You also want to pay close attention to the nature of the reflective surfaces of your sample. If you're working with something that's a rough powder or a roughened sample, that's all going to be diffuse reflectance, not an issue. It's when you have a mirror surface that can do a specular reflection and essentially maintain that overall intensity of the laser beam, that's when you need to be a bit more careful. So if you're trying to shoot your laser beam at a mirrored surface or something that's highly polished, then just keep in mind specular reflection can occur, so you need to keep your distance from that possible reflective event. The last thing that I want to mention, aside from the lasers, is that this whole isolation table, as well as the stage, basically has either pneumatic lift to basically keep it suspended with air, or it has motors that basically drive the stage around. And neither of those two systems care if you get your little fingers stuck in the way. So every single one of these spots right here on the air table is a pinch point. So you would never want to stick your fingers inside here, because if somebody leans on the table, crunch, you're going to get your fingers smushed right there. And this 800-pound table does not care that it hurts you. And by the same token, whenever the stage is moving, whenever you're translating the stage with a motorized fashion, please don't stick your hands or fingers or samples or tweezers in or around the stage when you're making those motions, because the motor will not stop just because you put your finger in the way. All right, so we are now in step 2 of our Raman SOP. This is the equipment startup phase. What we're basically going to do right now is do one more quick visual check to make sure that there are no potentially hazardous laser exposure risks before we go and turn on our lasers. And you don't have to turn on every single laser, you just have to turn on the lasers that you plan to utilize. So after a quick inspection, I can see that my tower, my lasers are still mounted in place. They're not pointing out at odd angles. Nobody has removed anything from here or lifted up the panel that allows me access to the optical cavity. No other notes in FOM, nothing about this tool being in service. So I know that I'm okay to proceed forward. There are no potentially hazardous laser exposure scenarios. So now I'm going to place this rolling curtain between the door and the Raman unit, just in case there's somebody that comes in. We don't want them to potentially have any kind of laser exposure. So you just roll this little guy in the middle of the room. He should stand himself up, and we basically just leave that to its own devices. Okay, so this guy's secured. Now I would proceed to switch on any of the lasers that I'm going to end up utilizing. Again, those are 532, 633, and 785. After you've turned on the lasers, please make sure you wait at least 5 minutes for them to warm up. And at this point, you can get ready to load up your calibration standard that we're going to utilize on the instrument. The first step that you would do to go through this loading the calibration standard is make sure the microscope stage is lowered all the way. And as you may remember, to lower the microscope all the way, I place my left hand on this coarse adjustment knob and make sure I rotate it towards me. If it doesn't move at all, that's great. It means that the last person lowered the microscope stage the entire way. The next thing I'm going to do is select the 10x magnification component. That's the one with the little yellow band on it, and I make sure that it's centered right in the middle of its field. Over here on top of the instrument, you'll find a little wafer piece that's marked silicon reference. So this is just a piece of single crystal silicon wafer. It's not the cleanest sample on the planet, and that's kind of by design. We want to have some kind of contrast on the top surface so that we can go find that surface and focus on it easily. And I'm going to show you that process in just a moment. So we place that sample directly on the little microscope portion, microscope slide portion of our stage, and just make sure you get it somewhere underneath this objective. You would then proceed to give yourself some topside illumination. Somewhere around 4 or 5 is probably fine. And then we're going to basically launch the software to provide us a video window so we can see the sample and focus in on it. All right, so my lasers have been turned on and they're warming up. I've set my microscope stage to the lower limit and loaded my silicon standard. And now what I need to do is get into the actual software program that allows me to get my camera feed so I can focus in on that calibration standard surface. That is the surface of our silicon wafer. If you walk up to the instrument and you find that the Windows login has not already been completed, the username that you'll want to click on that login screen is Raman, and there's no password. So in all cases, you should usually see the Windows login already done. And so the only thing that you have left to do is double click on this icon, which launches a program called LabSpec 6. As you do so, it's going to prompt you for your username and password, and those are credentials that you receive after successful completion of this training. And there we go. Once I get into the actual screen, I'm going to want to again launch a video feed in order to capture the focus position for my calibration standard. Depending upon the last time the power was cycled on the unit, it may also ask you to calibrate the stage. So this little pop-up is going to let the stage go to its XY limit positions. So our stage is going to start moving a little bit. He's going to go find his end of limits, and then he'll return back to where he started. What I want to do now is launch a video feed button by clicking on this little movie camera looking icon right here. And that will essentially give me another pop-up window from which I can then focus on my specimen. So I'm going to go ahead and click that now. All right, so now that we've got our video screen loaded up here where we can see it on our cool little double monitors, I'm going to start approaching the sample surface, again making sure that I have illumination turned up about to the midpoint, roughly 5, and I'm going to slowly approach the surface and look for changing contrast, specifically lightening contrast on my screen here. So when I was several inches away there, I wasn't capturing really any light back into my objective except for albedo, whatever bounces around the room. And so at this point, when I get near my working distance, I expect to see that this screen start lightening a little bit. That is getting shades and shades brighter. And then eventually we will see some kind of a focal plane that allows us to tell what's going on. Slowly focus on the surface of the specimen as follows. So again, 10x objective, slowly moving the coarse focus knob and watching the screen to see when it starts getting lighter and lighter by shades. And what that means is that I'm moving closer and closer to the actual working distance of this objective. And I should see some of the sample. So you can see it starting to get a little bit brighter, a little bit brighter, a little bit brighter, and now I'm starting to see little particles. I don't know if those are very clear to you, but there's 2 little dots here and here on the screen. So the first question you might ask yourself, well, is that the surface of my specimen? And the answer is I don't really know. I know I'm fairly close to the working distance, but the simplest way to determine if something on your screen is on the surface of your specimen is to move the joystick left or right just a little bit. And if those guys don't move, it means that dirt is on your objective or on your camera. So when I moved my joystick left and right, those guys did not move. So which direction do I need to keep going? Still further down. I'm going to go down even further. Oh, sorry. So closer to the objective, rather. There's some more dirt particles that I see right here. Now, if I move left and right on the screen, I still don't see those moving or responding. So we keep going a little further. There's another set of particles. Nope, not them. And then finally, this last set where I can start seeing things like scratches. Those are closer and closer to where I think I'm at the sample surface. So there we go. And now notice that the halo of the light started collapsing in. And if I translate left and right, you can see that those dirt particles that are on the surface of the sample, they move whenever I move the joystick. So that tells me that I just found the surface. All right, so I want to demonstrate for you one thing that you should really try never to do. I'm going to turn the light all the way up here, or at least brighter, and I'm going to focus past the point of the sample surface. So again, if I keep getting closer and closer to the objective, so now I'm at a spacing less than the working distance, and I just keep driving further and further and further. When you're using the 10x objective, nothing will happen because your stage can't go high enough up to crash into the objective. But as you go further and further, you can see what was kind of a focused white light ball is now starting to become diffuse once more. And eventually you see it turn into this weird looking series of dots. So all of these little dots inside here are the end pieces of the optical fiber cable that is delivering the white light from my lamp source into the microscope objectives. So what it means is that I'm now focused on something that is way past, so this is more like a reflection of that fiber optic cable, which I can wiggle around by moving this little knob right here. So if you ever see that image on any kind of fiber optic lit microscope rig, for goodness sakes, stop. You went too far, move the stage down. And again, how do I move the stage down? Thumb on top, rotate it towards me until I see something else, and just confirm that it does in fact move whenever I joggle the joystick back and forth. Now when you go to actually align the specimen at a higher objective, it's always best to align at a lower objective like this one, the 10x, and then switch over. So I'm going to do that now. So I'm going to switch over to the 100x objective, and now notice I went from something that was quite bright and in focus to now I got nothing. So the working distance is much more tight and finicky on this one. So one thing you may consider doing is turning up the white light source until you get a little bit of contrast. And now I need to go find focus again. I just translated a mechanical piece from the 10x position to the 100x position, so I haven't the faintest idea if I'm above or below the focal plane. So it means that I need to make an intelligent choice about which way to go to try to find focus. And the intelligent choice, again, is to always move the stage down. With the course control knob, that was place thumb on top and rotate towards me, that would move way too far for us to find focus using this 100x objective. So now I'm going to switch to using the Marhauser stage. And again, the safe direction is to rotate the knob clockwise. So I rotate clockwise, I can see that my screen is getting darker, 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 so that means that I need to go back in the other direction and try to find focus. But not so far that I see those little fiber optic bundle pieces. So I just move in little fits and starts until I see what I think is some stuff on the surface of my sample. Looks like it was right back there. Now I translate around. Oh, there was something. So there's a nice, helpful piece of dirt. So we're going to focus in on that piece right there. There's a little schmutz. Now I can go left and right. You see a bunch of scratches from tweezer marks and everything else on the wafer. So there we go. Now we know that we found focus. And again, if I had made a mistake and gone a little too far, it doesn't take long before you see that diffuse light start spreading apart, and then boom, there's that weird looking kind of, staring at a bunch of wasp eggs kind of a image. Again, that's the fiber optic bundle right here. That's why it's moving around when I play with it. So if you ever see that, remember you've got to go back down. So in this case, I'm rotating it clockwise to move back down to where I think I found focus on the surface. Right about there. And I got a nice scratch mark right down the middle of the screen. Okay, so that's basically focusing in on the surface of the silicon standard. So in addition to being able to focus optically, one other thing we can do is focus with the laser spot. And I'm going to try to show you what that looks like right now. This is an example of my system, which is focused in the 10x objective. You can see the size of the little laser spot right here. I'm going to go ahead and turn off that laser. So I just close my shutter. Now I'm going to change to my 100x field of view. I'm going to quickly determine my focus position. So again, I rotate the knob clockwise to move down. And actually, I'll need to increase my intensity just a little bit here. Now I'm going to go back in the counterclockwise direction because I see it getting darker, darker, darker. I'm going to rotate backwards and find the focus for this surface. So it's somewhere right about here. So I've got some features that are on the surface of the sample. You can see them kind of moving around in the background of the field of view. There's a particularly large piece of dirt. So now what I want to do is, instead of trying to focus on this surface optically using my own sort of contrast, I want to focus on it using a laser and just try to minimize the laser spot size because that's what maximizes my spatial resolution. So before I turn the laser back on, I'm going to go ahead and turn off my white light source so I can see it a little bit easier. And now I'm going to go in and click on the laser shutter. And we can see that that's where he's coming through right there. That's particularly weak. It's a little hard for me to see. Essentially what I have now is a laser which is going through a neutral density filter that is set to 0.01%. So I'm going to make that a little bit more intense and change it to 0.1%. And we should hopefully see a concomitant increase in the brightness. And there we go. So I know that I'm at a pretty good degree of optical focus, which is why the laser spot seems fairly small. What I'm going to do is I'm going to basically rotate my joystick knob to the right or clockwise, in which case we should move the stage down and I should be less and less focused, meaning that the laser spot should get larger on my camera field of view. So that's kind of what that looks like. Sort of a crossover. You can see as it moves back and forth between those two, there's sort of one optimal position where the laser spot is minimized. And that's right about there. And if I use the scale on my screen here, what it'll basically tell me is that that laser spot is somewhere on the order of about 2 to 3 microns in diameter, which is what I would expect for standard microscope optics. Okay. So you can focus either by optical contrast from a camera view or by minimizing laser spot size. In this case, you'll minimize spatial resolution and you should have the greatest amount of information coming back from the sample.